All right, welcome back. We are looking at lesson 3 from unit 1, and the topic that we are looking at today is continuity. So the goal is to look at what the definition of continuity is, and also we'll look at one-sided limits, some of the properties of continuity, and also the intermediate value theorem. So to kick things off, let's look at these pictures. They're quite lovely. And in all of these, it is not continuous. So our function f of x in this is not defined at this location. So our function f of x is not continuous at our point C. For this one, f of x doesn't have a limit because our limit, as we're approaching C from the left versus C from the right, those are different numbers, and so since those numbers are not the same, the limit does not exist. Limit as x approaches C of f of x then does not exist. And here we do have that our function is defined. F of C does exist, and we do have that the limit as x approaches C of f of x is defined. It does exist, but since those numbers are not the same, our function f of x is not continuous. So in all of these, f of x is not continuous, but the reasons are different here. We don't have our function defined at the location at C. Here, we don't have our limit defined at our location C, because our limit from the left and the right are different. And here, we have our limit and we have our function defined, but those numbers are not the same. Therefore, our function is not continuous. So those are the three things. And so the three things for having something continuous, a function is being continuous, the function has to be defined. It must exist. F of C must exist. Your limit as x approaches C of f of x also must exist. That function as x approaches C of f of x has to exist. And finally, your numbers have to be the same. The limit as x approaches C of f of x needs to be the same as what f is evaluated at C. If you have all three of these conditions met, then you have continuity. You can also have continuity on an open interval, and that's where you have these properties that are fulfilled everywhere on that open interval. And if you have it for everything on your real line from negative infinity to positive infinity, that's all the real numbers, then your function is everywhere continuous. So let's try this. Pause the video, discuss the continuity of each function. We have 1 over x, we have x squared minus 1 over x minus 1, and this piecewise function, and also good old sine. Pause the video, think about the continuity of each of these. So for f of x is 1 over x, well, if we're looking at the limit as x approaches 0 of 1 over x, that means that we're getting closer to 0 from the right and from the left here as our denominator. But when we have 1 divided by some very small number, but it's a positive number, that means that our function is going up to positive infinity. But if we have, so that's when we're approaching 0 from the right. If we're looking at 0 from the left, that means that we are taking 1 divided by a very small negative number. Therefore, we are going towards negative infinity. Therefore, this function f of x does not have continuity at x equals 0. It does have continuity everywhere else. And if we want a quick sketch of that, we do have continuity everywhere else, but here at x equals 0, it is not continuous. For part B, we're looking at x squared minus 1 divided by x minus 1, and you should be thinking to yourself, okay, this is something where we could use what we learned in the last section about continuity, about looking at limits analytically. So we have a difference of squares, so x minus 1 times x plus 1 in our numerator, and in our denominator we have x minus 1, and I threw that in parentheses so that we could get this. And so this is equal to the limit as x approaches positive 1 of x plus 1, which is equal to 2. So we do have our limit existing at x equals 1, but if we try to plug in 1 into g of x, we get undefined. So we don't have continuity at the when x equals positive 1, but we do have continuity everywhere else because it looks like that line. The only problem is that we have a hole. What about for h? We have a continuous function here, right? That's just a line, x plus 1, which we looked at over here. And then we also have e to the x, and e to the x is something that looks kind of like that. And I guess it goes up more steeply. So when x is less than or equal to 0, then we are looking at this function. And so we're going this way. This way. And then e to the x is when x is greater than 0, so that's looking at this part. And so those are both continuous, right? If you're just looking at that, then you can see those are both continuous. But do those limits equal each other? Well, let's think about it. Limit as x approaches 0 from the right of e to the x, and the limit as x approaches 0 from the left of x plus 1. What happens here? Well, we get 1. And what happens here? Well, e to the 0 power is just 1. So looks like those match up, and we are happy because that means that our function is continuous. So h of x is continuous, and I think it's continuous everywhere. One more. If we're looking at sine of x, just a quick sketch of that. And that just keeps on going, right? I'm going this way as well. Make sure we do know how to graph our sine and cosine functions, also tangent, which is sine cosine. So if we have sine of x looking like this, okay, well, no matter what x value we plug in, we are always going to get out a number, and it looks like this is a pretty smooth, continuous graph. So we can say this is everywhere continuous. Everywhere continuous. So for all real numbers, our function is continuous. So let's now look at one-sided limits. I was using a little bit of this notation earlier, but we'll just formalize it. Or we'll reiterate it, I guess. So we have x approaching c from the right. That means that we have a little plus sign as our superscript on c, which is in our limit, like underneath our limit notation, and that's thinking about a limit from the right. So we're going from the right to the left. We're approaching our location from the right, and that is going to give us a number, hopefully. If not, then we have other things going on. And if we have our x approaches c from the left, that means that we have a superscript negative because it's coming from the negative direction, and that is also going to give us out a number, hopefully. So limit from the right, limit from the left. Over here, find the limit of f of x equals root 4 minus x squared as x approaches negative 2 from the right. So this is going to give us what kind of function? Well, this looks like it's going to be a circle, but with the square root, we're also only going to look at the positive side of our circle function. And so let's look at this. So here we have on Desmos, and I took off some of the things like the grids, and I made the font a little bit bigger. But if we're approaching negative 2 from the right, then where are we getting to? We're getting to 0. Now, if we look at that analytically, then we're looking at the limit as x approaches negative 2 from the right of square root of 4 minus x squared. You can just plug that in. And what do we get? We get root 4 minus 4, which is root 0, which is 0. Cool. And what we're approaching from here is coming from the positive direction, so we don't have a breaking of our root symbol. So in our next example, we are looking at the greatest integer function. The greatest integer function is very helpful because it's a way of taking something that is continuous, like the real numbers, and breaking it up into discrete parts, like the integers, because integers don't include anything in between the different integers. Between 0 and 1, there's an infinite number of numbers, real numbers, right, because of the density of the reals. But with our greatest integer function, we're just taking all of those inputs and mapping them to the greatest integer, which if you're more computer science minded, that is the floor function. So going back to this, I'm going to take this off and put the floor function on. I just typed in floor, parentheses, and then this is what came up. So if you're looking at what's happening around 0, if we're approaching 0 from the left, where are we coming to? We're getting to -1. And if we're approaching 0 from the right, where are you getting to? We're getting to 0, because we are looking at the greatest integer. So if you're looking at 1/2, the greatest integer that can get you to isn't 1, because that would be going up. The greatest integer that can happen is going down to 0. This is I guess a shift on the ceiling function, which is looking at when you're rounding up, what that can get you to, and that is a shift on the floor function. So let's look at it more analytically now. So if we were thinking about the limit as x approaches 0 from the left of our greatest integer function, which in this book we are giving it these double brackets. Some books like to do this, and then you can also just say the floor function. That's also fine. So that is going to be -1 when we're approaching 0 from the left, because if you're plugging in, I don't know, like -1/2, and you're going to the greatest integer that has, that's going to give you out -1. And if we're looking at the limit as x approaches 0 from the right, so we're approaching from above, on our greatest integer function, that's going to give us out 0, because, for example, if you had +1/2, and you're looking at the greatest integer that can happen there, that is going to go down to 0. I've said a couple times about like that limit existing or that limit not existing, and I'm just formalizing that. So when we have the limit as x approaches c from the left of f of x is equal to a number, and the limit as x approaches c from the right of f of x is equal to that same number, then that limit exists. So this is an if and only if, is our mathematical like shorthand for that, but if and only if, and that is also meaning that we go both ways. It's not just that P implies Q, but also that Q implies P. Therefore, P and Q go this way, if and only if. Up next, we're thinking about the properties of continuity. So if we have some real numbers and we're looking at some continuous functions, then they behave like we think they will, because numbers behave the way that we think they will. When we're taking some scalar multiple, then we're still getting a continuous function. When we have a continuous function plus another continuous function, or a continuous function minus another continuous function, then we're still getting a continuous function, because we're getting numbers plus or minus different numbers, and so that will still yield a continuous function. The products, when we're multiplying two continuous things together, then we are still going to get continuous functions. And quotient, so if we have a continuous function divided by another continuous function, then we are going to have the output be a continuous function as long as our denominator is not 0, because remember, you are not allowed to divide by 0, because then you get something that is undefined. So let's look at the interval or intervals for which our functions that were given are going to be continuous. The tangent of x, that has asymptotes. Where does that have asymptotes? Whenever cosine is equal to 0, and that is at the pi/2's, and then the plus every pi of that. So k pi, where k is an integer. Or bold on the z. It's a really bad black. K is an element of the integers. So that is where we have discontinuity. Everywhere else we do have continuity, because we are having a tangent that just looks kind of like that asymptotes there. So our intervals on which this is continuous is all of where these are. So, right, we have like pi over 2 to 3 pi over 2, and so on. G of x is sine of 1 over x when x is non-zero, and 0 when x is 0. When is this going to work? Well, we have a composition of functions. We have sine of 1 over x, and this is going to be 1 over x is continuous everywhere except for at x equals 0, and we looked at that earlier. When we're plugging those in, though, what do we get as we're getting closer and closer to 0? Well, if we're approaching 0 from the right, then we're looking at sine of infinity. If we're approaching 0 from the left, that means that we're getting sine of negative infinity. And both of those oscillate. They oscillate a lot. So even though we do have our function is defined at x equals 0, the limit as x approaches 0 of g of x does not exist. And the cute name for this is a growl function. And then it comes down. So here, our limit does not exist. Okay. One more, looking at x times sine of 1 over x when x is non-zero, and 0 when x is equal to 0. Well, this is actually, we looked at this before, kind of, where we're looking at the Squeeze Theorem. So we can think about this as sandwiched between two different functions, where we're looking at, well, we have x, we're looking at x times this part, and this is what's going to oscillate, but we can look at this bounded between the functions negative x absolute value and h of x and positive absolute value of x, because this sine thing is getting is oscillating between 0 and 1, and x is just x, so we're multiplying that by something that's kind of oscillating between 0 and 1, then we can bound it above and below by plus or minus our absolute value function. So that means that our limit does exist. Our limit as x approaches 0 of h of x exists, and it is 0. And h of 0, we're told here, is equal to 0. Therefore, our function is continuous everywhere. Fantastic. Oh, so I forgot to say that g is not continuous at x equals 0, and this is continuous everywhere, all the reals. All right, so now I'm going to tell you a story about when I drove to Chicago from Maryland to get married. It was super fun, but driving from Maryland to Chicago and back was, let's say, a 12-hour endeavor. So if I started driving from Maryland, and then I drove through the night, so I went from 8 p.m. to 8 a.m. according to my car clock. So that doesn't include the time change that happens, because Maryland is in Eastern time, Chicago is in Central time. So 8 p.m. to 8 a.m. that's when I drove. And let's just, for the purpose of all of this, let's say that there was only one route going from Maryland to Chicago, because I just didn't want to pay the tolls that were happening in some parts of Ohio. So there's only one way to go there, Chi-town. And so, and this was Sunday evening into Monday morning. And then, got married, woo, super fun. And so then I started back driving from Chicago at 8 p.m. on Sunday and got back at 8 a.m. to Maryland. My question to you is, was there a location in between Maryland and Chicago where I was at the exact same location and my clock in my car read the exact same time. So pause the video, think about it, and we will come back. So yes, indeed, there was guaranteed a time, because if you think about, yes, say like distance from Maryland to Chicago, so going this way, that's what the clock was reading, 8 to 8, which is a bad use of graphs, but that's okay. And then coming back, I went starting as far away from Maryland as possible back. I got stopped for, going above the speed limit, and then got back to Maryland. Well, there is inevitably a intersection of those two curves because, space and time are both continuous. Therefore, that intermediate value has to exist. And that is our segue into the intermediate value theorem. The intermediate value theorem is, I would say, a 3-star theorem. So write that down in your notes, intermediate value theorem, IVT, as some people like to call it. But, you can also just call it intermediate value theorem. It's saying that if your function is continuous on a closed interval, and you have a number that's between your y values. So let's start drawing a picture of that. We have our interval from a to b, and we have our function is continuous there. So let's just say it goes like this. Okay. And then we have, this is f of a, and this is f of b, right? Because we have evaluating points right there. And you have a k. K is in between f of a and f of b. So k is a y value. Then there exists at least, this is an existence theorem, there exists at least one number c, in between a and b, on that interval between a and b, such that f of c equals k. This is an existence theorem saying there exists an x value that fulfills the y value that we have. So, use the intermediate value theorem to show that the polynomial function f of x equals x cubed plus 2x minus 1 has a 0 on the interval from 0 to 1. So what does that mean? That we have a 0, a root that exists between 0 and 1 on our f of x. So first, we need to establish what our f of a and f of b are, because we know that a is 0, right, and then b is 1, because that's the interval that we're given, and a and b are x values. Now, f of 0, what is that going to be? We'll just plug it in. So we got 0 cubed plus 2 times 0 minus 1, and that's a negative 1. Lovely. We love that that is a negative number. Hopefully, f of 1 gives us a positive number. So we get 1 cubed plus 2 times 1 minus 1, and we do indeed get a positive number. We get 2. So if we're going to draw a picture of this, that means that at 0, our function f of x is evaluated at negative 1. And at 1, at our x value of 1, our y value is positive 2. Since we know this is a polynomial, we know that there is continuity in between 0 and 1. Therefore, we also know that since 0 is between negative 1 and 2, which are our f of 0 and f of 1 values, then by the intermediate value theorem, there exists c in our interval from 0 to 1 space, such that f of c equals 0. So this is guaranteeing that we do have a root or a solution or a 0 on our interval from 0 to 1. And there's something I had down here. Yep, bisection method. So the bisection method is a root finding method, and there are lots and lots of different root finding methods. it might be interesting to look at, but that is something that you could learn more about in a class called computational methods, or if you're on the internet, you could also find it under something called numerical methods. And so the bisection method is effectively looking at an interval where like in our previous function, from 0 to 1, we got a -1 and we got a +2. So what you do is you take the interval where you are guaranteed by the intermediate value theorem that there is going to be a 0, you cut it in half. So you look at 1/2. Evaluate your function at 1/2 and see if it's going to be positive or negative. If this is positive, then your new interval that you're looking at is this. And that took your entire interval that you were trying to find your root in and cut it in half, which is fantastic. That's why it's called bisection. If, however, your value at 1/2 was negative, then you would still do the same cutting in half, but you just look on the other interval because you're guaranteed that there's going to be something there. So depending on what happens at your midpoint in your bisection spot, that alters where you continue to search. And it is not terribly inefficient, but there are better ways. So if you are interested in something to journal about, root finding is rather important. All right, so in this video, what did we see? We looked at the definition of continuity. We looked at one-sided limits. We defined some of the properties that happen with continuity. And then we talked about the intermediate value theorem. Right, bye.